collapse, the drones collapse itself. So, the drone is not capable of supporting for long time the functionality of a substantially base station, the hub that collects information coming from different kind of sensors, some of them also in broadband using the LTE. It's not, therefore, we considered the possibility of splitting some function, removing them from the radio head end in the drone, and virtualizing them inside the unmanned aerial vehicle. That will be the tested solution, and the test solution on site, because we have the availability of a big unmanned vehicle of the civil protection of Trento. But at feasibility study level, we are investigating the possibility of virtualizing some network function inside a satellite cloud, and in particular using the CubeSat to host the BBU, the baseband processing unit. This solution would be potentially very effective. Indeed, the NATO was very interested in this. Indeed, the satellite can manage overall the network, because it has the overall network control, because it's placed very high on the sky, and so it has a very large footprint. It's the ideal node to manage the virtualization of radio resources shared by some devices. The problem is the latency. Remember that in the old picture, that I've shown at the beginning of the presentation, that the splitting of functionalities from the radio head end to the baseband unit has throughput and latency constraints. We measured the latency. The latency of the CubeSat, involuntary CubeSat, is of the order of 2, 3, maximum 4 milliseconds. At least tolerable, at least. The latency of a geostationary satellite is of the order of half a second. That is not possible. So a geostationary satellite is better to host complicated processing architectures, but the latency avoids this. So, in these last days, we preliminarily analyze in quantitative manner the impact of the latency, considering the slicing, where the turbo decoding is moved from the radio head end, from here to the satellite. So we need a satellite link transmitting from the drone the coded stream, and the decoding is performed inside the CubeSat. Then the downlink is forwarded from the CubeSat to the remote control center. I put here again the picture, just to remember it. And we are in this situation. Throughput 180 megabit per second, okay. We designed the satellite link in order to, the CubeSat link in order to cope with this constraint. It's not impossible. it's a bit expensive because we need high gain antennas on the CubeSat. But now in the CubeSat there are prototypical antennas based, for instance, on inflatable antennas developed by the JPL that allows gains of the order of 25, 27 dBi. Yes. Not commercial technology. But we are not speaking about a commercial system here. The NATO is funding for technology that will become civil technology, not military, but technology of top level for safety critical applications. Therefore, the cost of the CubeSat and the cost of the drone will be not of a few euros, by the way. This solution has been studied, not implemented. It's only studied in lab. But the problem is the latency. Because the operation, in order to perform the slicing operation, we should perform the complete coding and complete decoding operation in a given delay. In our system, we decided to use not to use the conventional HRQ mechanism of LTE, but because the LTE forecast is to transmit the packet and then to receive the acknowledgement or the not acknowledgement. In this configuration, this kind of approach is severely limiting because we have a latency here that is too high. So we decided to use another mechanism that is forecasted by LTE. So not using the ACK-NAC reception, but using a very robust turbo coding in order to correct all errors with a high probability. So the probability of having bad information is limited. For instance, using the turbo coding at rate 1/3. If we use this turbo coding, we limit the spectral efficiency and the throughput, but we don't need the ACK-NAC mechanism that limits the throughput itself. So the probability of error of the turbo decoding depends on the channel, F bar depends on the channel, on the number of turbo decoding operations, and on the signal-to-noise ratios. Typically, on AWGN channel, now that the figure is not well displayed, but in case of zero, in case of no turbo decoding, we have this bit rate curve. For 2, 3, 4 iterations, the bit rate curve improves and improves. After 5 iterations, generally the curves do not improve, do no longer improve, because the turbo decoding converges. Okay, but in order to make the slicing operation with the turbo decoding on the CubeSat successful, K should be equal at least to 1. So the turbo decoding should perform at least 1 iteration. Otherwise, if we have no time to perform the iteration, the operation fails. How can we evaluate the number of iterations that we can perform? There is a formula reported in this recent paper. The list of the parameter is reported here. P is the computational power of a single BBU processing unit in a giga operations per second. O is the number of processing units installed on the BBU and working more or less in parallel. F is the available delay budget needed, that is a constraint of standard. So in order to, in the LTE, the turbo decoding operation must be completed in 3 milliseconds, otherwise the networking cannot work. J is the time required for our wireless function, for instance, the synchronization. There is a standard value that is imposed. D is the link delay between the radio head and the BBU. And the T processing is the time to detect the onboard, the turbo-coded block that is typically equal to the bit rate, to the link bit rate from RH and BBU, and the number of bits of the block. In our case, the time should be is imposed by the bit rate, and that was 181 megabit per second. The L is the turbo-coded block length imposed by the LTE, and finally F. Oh, sorry, I repeated the 2 letters. F here, no problem. This F is the number of elementary operations required per decoding iteration. No, sorry, was a mistake, a typical typo. And this figure is obtained fixing P equal 1.2 giga operation per second, and F equal this F equal to 3 milliseconds. This picture reports on this axis the number of processing units installed on the BBU from 1 to 10, and on this axis the BBU RH link delay, so the delay imposed by the link between the satellite, the CubeSat, and the drone. For delays longer than 2 milliseconds, no iteration can be done. The turbo coding, the decoding operation fails. For a delay less than 2 milliseconds, the number of iteration increases with the number of processing unit as expected. So, in order to produce, in order to make the operation feasible, we should design the orbit of the CubeSat, the elevation angle, the orbit altitude, in order to make the link delay from the RH and the BBU compatible with the bound of 2.1, 2.2 milliseconds, in order to allow, during the visibility, the time of visibility of the satellite by the drone, to have a delay contained in an acceptable value. We perform some experimentation with different modulation and turbo coding rates. Substantially, with a 4 QAM modulation and coding rate 1/3, considering a signal-to-noise ratio of 9 dB. This signal-to-noise ratio is imposed by a link budget of the connection from the earth sensor to the drone. Actually, if we succeed to do one iteration, we have a bit rate always less than 10 minus 8. So, but this arrangement has a spectral efficiency of less than 1 bit per second per hertz. With the 16 QAM, if we perform only one iteration, the bit error rate is higher, 1.3 per 10 at minus 5, using the same coding rate of 1/3, with a bit with a dB over a knot that is lower because we are using a higher order modulation. So during in this case, during the whole flight time of the CubeSat, substantially the LTE, the turbo decoding, performs the expected performance, because as soon as the CubeSat approaches reduces the distance with respect to the drone, the number of turbo decoding iteration that can be performed inside the CubeSat increases and increases, and therefore the bit error rate improves. In the case of 4QAM, it's enough to have one iteration. So for all the time of flight time for each orbit altitude, we have our performance. 10 minus 8, we can transmit everything, also video. For the 16 QAM, the performance degrades. If we consider 64 QAM, the performance are much worse. By the way, this is true. The latency is the critical parameters, because if the latency between this connection